Hi, I'm Edwin Sanjaya. I'm a junior in Aerospace Engineering Department at the University of Michigan. This summer, I'm working with Professor Girard, Professor Kabamba, and 3 graduate students on efficient modeling and algorithm for dynamic force level resource management. So let's talk about a war settings. In a war, a quick, optimal decisions making process will be critical in order to beat any enemy threat. So we create a program that provide us a set of optimal resource management decisions. And to achieve this, we are using a dynamic programming. So what is dynamic programming? Dynamic programming solves complex problems by breaking them into simpler subproblems. There are 3 governing equations related to dynamic programming. The first equation here on the slide is determining the next state based on the previous states and control input u. This is the state transition equation. The second equation is called the Hamilton-Jacobi-Bellman equation. So by solving J star, we will minimize the sum of the incremental cost phi and the optimal future cost to go. The last term on the second equation here is actually the J star of the next step. So this explains that the dynamic programming works backward. It works from step n-1 to step 0. And then the third equation, the u star, is the argument of the second equation. So from the third equation, we'll get the optimal policy that corresponds to the minimum cost in the second equation. So let's talk about a sample war scenario. So as you can see from the grid picture on the slide, there is a red diamond represent the enemy force is a static target. So the enemy cannot shoot or cannot move. And the friendly force is the blue ship that can only move or shoot. And the ship can only move one grid at a time and can only move to 4 directions: up, down, right, or left. The ship can only shoot the target from the corresponding grid around the target. There are also multiple hazards represented by the black square. So the ship will be dead if it hits the hazard. So how to solve this sample scenario problem? So first we need to define what is the state machines. This is only the simplified version of the state machines. So first we start from when the ship is alive and the target is alive. So when the ship moves to the other grid point, the ship is still alive and the target is still alive. If the ship moves to the hazard, the ship will be dead and the target is alive. If the ship shoots the target, then the ship is alive and the target will be dead. On this slide here, show you the result of my dynamic programmer, about how the dynamic programmer solves the problem. So as you can see, the ship moves to the target and kills the target. It takes the shortest path to kill the target to make sure that we kill the target as soon as possible. So what we learned from this research, the dynamic programming has for the finite state machine has the potential to solve the force level resource management problem. However, we also learned that dynamic programming is computationally expensive. As the size of the problem gets larger, then the time needed to compute the optimal policies increase exponentially. So this is called as the curse of dimensionality. So this brings me to the future work. So the future work will include implementing approximate dynamic programming to reduce the time needed for the program to calculate the optimal policies. And then the other future work will include creating a more practical battle scenario. So for this video, I also want to thank you to the SURE program to give me the opportunity to do research with faculty member at the University of Michigan.